Well, good morning, ladies and gentlemen. Our first session today will be the morning session, and I'm going to get Peter to swap over so that we can link into the next slide presentation. It's really interesting. There's a lot of people in this room who spend a lot of their time doing reviews, and it's really interesting to understand what people think of QA/QC. And as reviewers of lots of projects, I'm constantly bewildered by what some people think or don't think constitutes QA/QC. So a few talks today will be people on their hobby horses, and there's some really good presentations. So I've started the day with trying to set the scene, probably talk a little bit about one of my hobby horses. What? Okay, so to start off, let's talk about some definitions. We all think we know what QA/QC is, but fundamentally it's all around quality management. It's a system that integrates both quality assurance, quality control to deliver products and services. And that's a really important thing when it comes to the exploration and mining industry. QA, there's obviously lots of definitions. This is the definition that I've picked out. That part of the management system that's focused on providing confidence that quality requirements will be fulfilled. The planned and systematic activities in the quality system that provide confidence that a product or service will fulfill requirements for quality. And the QC part is that part of the quality management focused on the operational techniques and the activities used to fulfill requirements. And it's so often you see in the minerals and exploration mining industry that the focus is very much on that QC side, not necessarily the QA side. So let's think about why we're all here. If this is not our goal, we're in the wrong business. We're here to understand mineralizing systems, discover something, and get them into production. That's the only function of exploration and mining industry. Our goals may be different. As a person and a geologist, we might be here to make the world a better thing. We might be here to become rich and famous, and we might want to help to contribute all of the metals that society needs going forward. So let's think about where QA/QC is relevant in this stream. Well, from my point of view, every step of the way is absolutely important when it comes to QA/QC. It's relevant across the board. Doesn't matter whether you're an exploration manager ruminating about the next concept that you have for an exploration model and an exploration target, there's QA/QC involved in that all the way through to production. And the QA/QC systems evolve. I like to use the word that they need to be fit for purpose, and other people in the room are probably going to disagree with that, but that's my requirement for a QA/QC system. Nothing fits everything. It will be sometimes subjective, sometimes objective, sometimes qualitative, sometimes quantitative. Certainly, it tends to become more quantitative as you move from exploration through to mining because there's physically more data there to play with. So let's think about now what the data inputs are. As geoscientists, we have a whole range of data inputs that contribute to the exploration and mining process. And today, a lot of the focus is around these data inputs. However, we've got to analyse them. We've got to use our knowledge, our skills, our experience to interpret, to model, to estimate, and to predict. And so QA/QC, in my opinion, covers the whole gamut. And we need to think about QA/QC as a process that we focus on our data, but we also have a process focusing on our actual analysis. So what are the typical tools of trade that we might use and might have at our disposal for those sorts of processes? Well, we have lots of standard operating procedures. They're trying to set out the scene for collecting data, having a process that will result in good quality data. We have reviews. Reviews get done everywhere along the way. We have appropriate calibration of equipment. We have the sniff test. All geologists will look at data and say, does that actually seem reasonable to me? That's all part of a QA/QC system in my mind. We have all of the statistical tools, and a lot of that we're going to cover off on today. So a lot of the talks today are focused on this part of the tools of trade. Assessment of alternative interpretations of the data. That's a fundamental part of QA/QC. You want to make sure that, yes, you've come up with an interpretation or an analysis. Is it reasonable? Is it the best? Is it justifiable and demonstrable? Internal and external reviews. Certainly as projects progress, these become really important for a lot of companies. And more. And today's focus really is all around the more. So I'm really looking forward to today's presentations. So to finish my setting of the scene and my hobby horse, this is the thought for the day. Quality is never an accident. It is always the result of high intention, sincere effort, intelligent direction, and skillful execution. It represents the wise choice of many alternatives. So with that, I'd like to introduce our first real speaker of the day, and that is David Arnott. David is a qualified geologist with 35 years of international mining industry experience and is a CASA certified remote pilot managing UAV surveys for the past 10 years. So please welcome David to the screen. Thank you.
Thanks, Mark. Morning, everyone. I think I'm on, yeah. Okay. Morning, everyone. Appreciate the invitation, Mark, to come along and speak today. And I'm actually going to talk about a hobby horse today. It's something that I got involved in purely by accident in the work that I was doing in the geology and mine planning space. And it got to the point where I was looking at the information that I was being provided with to do work with and really starting to question the veracity of that data and saying, I don't think it's right. And so I actually ended up going down the track of actually saying, if you're going to do a job properly, do it yourself. And so I actually ended up learning how to fly a drone, got accredited to do it, and actually went through the process over 10 years of realizing what the challenges were and understanding then what needs to be done to get quality information. So what I'm going to do is take you through some of that this morning. It's a pretty rapid fire presentation. I think I've only got the 20 minutes, so let's kick that off. Okay, so UAV or unmanned aerial vehicles are used for a variety of different surveys. One of the key areas that I suppose a lot of people work in, and because the equipment can be relatively inexpensive to start off in, is getting into things like photogrammetry and LiDAR type surveys. Once you start getting into things like multispectral and hyperspectral scanning and some of the sort of the geophysical tools, and you're hanging those things off drones or other sorts of unmanned aerial vehicles, and it may not actually be in the air, it may be on the water or something like that, or even underground, the payload starts to get very expensive and the equipment starts to get expensive. As the payloads get bigger, you essentially end up with bigger drones and more expensive to run and operate. But so some of the focus we're doing is we'll be talking about this sort of photogrammetric and LiDAR, which is where a lot of people sort of work. And look, one of the key things with the data that we work with is about getting it geo-referenced. So that's really important. If it's not in the right location, you're not going to be able to make it interact correctly with other forms of data that you're bringing in. And so this is where the main part of the topic that we're going to talk about today is ground control sort of comes into play. So as I said, look, there's bunches of UAVs out there. Entry level, really inexpensive. You can get in and you can be operating a drone for less than, maybe $4,000 or $5,000 and capturing high quality information. There's a bunch of exclusion categories that allow you to do that without licensing as well. So, it can be a quite inexpensive and rapid way to capture data. But as I said, you start going to the other end of the spectrum where you're getting in more specialized equipment and it starts to get quite expensive. But the advantage of UAV is that you can get information really quickly. You're not relying on having to organize an aircraft, organize a pilot. Quite often you don't need to get airspace control unless you're working around, say, an aerodrome or something like that. And because you're flying at relatively low altitudes, the quality of the data that we see today is far better than what we would traditionally have seen. And I can see there's people who got as grey hair as I have in the room when we were working with stuff that was coming out of stuff captured on planes. So, you know, you can produce information like this, but how do you know it's accurate? Like in this image here, you can pick up that there's vegetation that's been dumped in the overburden pile. The imagery looks okay, but is it actually geolocated correctly? We don't really know that. And quite often in, I suppose, the role that geoscientists play or mining engineers play, we're not capturing that data. We're just being given a product. And unless we actually understand what the QA/QC processes were that were used to capture that data and process that data, we just take it at face value. And sometimes we wonder why, you know, things don't end up where they should end up. So what sort of things can influence, what sort of factors can influence accuracy? So there's a whole bunch of things that can occur, both in the planning, how you collect data, the execution of capturing that data and the processing of that data that will impact that accuracy of that end product. I use the analogy that it's like plan, plan, plan. If you plan everything, you'll usually get a good outcome. It's when you don't plan, that's when things start to go awry fairly quickly. You know, we can talk about accuracy, we can talk about precision, and what I want to now start doing is talking about ground control points. So they're also referred to in the industry as GCP. What are they? They're just known points around your site or wherever you're surveying that you know what the X, the Y, and the Z, or the easting, northing RL, or latitude and longitude, whatever it is that what coordinate system you're working in. But it's known with survey grade accuracy, okay? This is the only thing that you can use to cross-verify against other data that you're capturing. So everything else that you're going to capture, you're relying on a GPS that the drone's picking up. This is independently collected data from some other process that's survey grade accuracy. So what are the good things about a ground control point? And you can have good ground control points in a lot of the audits that I've been doing over the last couple of years when I've got involved in this space is there's a lot of ground control points out there that are really bad, that have been poorly designed. They were possibly designed for high altitude aerial photography where the resolutions are a lot, you know, you're using flight heights are a lot higher. The resolutions of the equipment weren't as good as what you're seeing in today's sort of cameras. And so you end up with this inaccuracy and that sort of thing. So what you want is something that appears two-dimensional in form. It needs to be on the ground. That's why it's called a ground control point. Don't know how many sites I've gone and looked at and they've got ground control points positioned on tops of blocks. And they have them on tops of blocks because that way they don't have to go around and cut the grass that grows around them. But it creates an issue. So you need something that you can pick with repeatability where that location is. Okay, the quality assurance side of it. What do we need to do? What are we going to do and what processes are we going to do to make sure that we end up with a quality product? Okay, big things to look at. What we've got on the screen here. Use current technology, okay? If you've got people that are surveying for you that are going, oh, you know, I'm just sort of getting into this, or, you know, this is all I can afford, and they just go and buy a drone with no sort of RTK type processing capability on it, then automatically it's like having a drone that's got a Garmin handheld GPS on it. It'll be as accurate in the XY by about plus or minus 3 meters at best. In terms of its elevation position, that drone could be anything from 20 to 30 meters out in elevation. So you know when you go with a handheld GPS on the ground and you use that sort of technique to pick up a location, it might be okay in the sort of exploration sense for getting a field location, but if you want precision, that won't work. So what we want to do is people to use equipment that's appropriate, but also back it up with some other process. So they talk about RTK, which is real-time kinematics, and they talk about PPK as post-processing kinematics. What you want to do is actually join those two things together and do both of them. And then that crossover between doing both things will actually give you an informed survey, and you're putting in these redundancy systems into play, because RTK will only work when the drone is actually being able to speak to the controller and the base station. And quite often in certain terrains, that break happens a lot. You end up with a break connection between that UAV and the base station device, and you start to lose that GPS information that is giving you the accuracy. So you just basically fix it up by doing a PPK process and include ground control points in your survey. Okay, as I said before, avoid placing objects on the ground, or sorry, off the ground. Here's I suppose, an example of what happens when GCP are placed on some other sort of object. So in this instance here, we've got a concrete block that someone thought, that's a great place, we'll put that, we get grass that grows around this site, causes some problems. We'll pop the ground control point on the top, and then post-process filtering that's run over the algorithm when it's actually stitching the models together takes out man-made objects. Quite often people want to take man-made objects out because you might be doing some reconciliation studies on stockpiles that are out on a site. Maybe you want to pull equipment out that you don't want to see that in your model, and you want to make it easier from a mine planning perspective to be essentially working with a machinery-free and infrastructure-free model. Well, those sorts of post-process filters can cause you a whole lot of grief. So it's put GCPs on natural surfaces. Maintain them, okay? Like everything, it wears out, and particularly in, I suppose, environments like Queensland, where we have extremely hot summers, we have lots of times of rain, like heavy rainfall, then, you know, having a ground control point like this and telling someone, can you pick that actual crossover point in an image that was taken 120 metres above the ground? Probably not, in all reality. So go out and maintain them. Again, using structures like that, I don't believe is best practice. Get them back onto the ground. Utilize commercial stuff. I've gone through the process as someone who has learnt the skill of how to do this, of creating my own and thinking, oh, look, I've come up with this great design for something, and it only cost me like $40 to produce it, plus all my time, and I've got to go down to Bunnings and I have to carry heavy equipment around and build these things. Just go out and actually buy them. You can buy them way cheaper than you can manufacture them yourself, but make sure that the design is something that is actually unique within the environment that you're working within. In some environments, yellow is not a great color. So make sure that whatever your environment is, particularly if you're doing photogrammetric work, that you pick your colors correctly. Some of the advances now that are sitting in the AI space in terms of processing mean that if you actually use regular patterned GCP, the software product will do the picking and determining where the location of that ground control point is within that pixel map on a photo. In the same way, though, you're going to use ground control point in LiDAR imagery because, again, you've got to reference the LiDAR back to something. You've got to have some knowns on the surfaces that you're trying to model. In the same way, if you're doing hyperspectral scanning, you need to be able to place that hyperspectral map somewhere in space and understand possibly what the corrections are. They're going to be related to altitude with flying. So you need to have that ground control point data. Cannot be understated that you need this stuff in any of those surveys that you're preparing. Okay, so then what do we do? How do we identify defects? Now, unfortunately, as end users, and a lot of us are, we just see the end product. We don't actually get to see what the product was that was captured and gone through a process of generation to produce the models that we use. So how do you identify those things? Typically, look, if you can get access to post-processing reports that came with information that's given to you, review those post-processing reports. Do not trust everything that you're given. I've been looking at some stuff recently that will really make your hair curl, and it's just people just going tick and flick. They want a model. I'll give them a model, but no understanding that we want a quality model. If you're paying for a gold service, expect to get a gold star product with it. What can you do and this is just looking at the photogrammetric space, look to see if you've got areas that are underexposed or overexposed, okay? Ideally, if someone's going to photo or capture imagery, they're going to do it when the sun angles are high in the day, so that you actually have got a limited amount of shadow occurring in your imagery. Also, you'll find that you'll get pilots sometimes go, oh, I can get 3 or 4 surveys in at different sites, and they'll push it from sunrise to sunset. You want to be getting your capture taken in the middle of the day. And most times, some of the metadata will actually tell you when the photography was taken for a site. So try and get high sun angles. Try and avoid getting blurred imagery. Quite often people will rush through a flight and actually try and, particularly at low altitude, if you get the speed wrong, you actually get forward motion blur on your images, and that creates essentially an inaccurate model because you can't get that precision and understand what those pixels are doing in the imagery. Look for holes in your terrain surface, so avoid the edges of your terrain model. Make sure that if you've got a model, that the model always extends well beyond what you actually want to look at, because the edges will tend to be a little bit sort of flappy. They blow around in the breeze somewhat. And also, look, make sure that it's in the correct reference system. One of the big things now that a lot of systems are transitioning over from GDA 94 to GDA 2020. We're seeing old data sets being plugged into new reference systems without getting put through a data transformation. So check your metadata, make sure that the metadata is telling you you're in the right coordinate reference system. In the same way when it's being processed or it's being captured, most of the capture is done in WGS 84, but it needs to be processed in the correct reference system. How do you know you've got something wrong? If you've used ground control as part of a survey, and you can put ground control in post-surveying and post-processing, and you can actually check your model, the industry standard for testing it is what's called root mean square error. So essentially all we're doing is we're looking at the variation at known locations in elevation between a control point and the model that's been produced. Really simple. You can do this sort of stuff inside Excel. What you need to do, though, is have ground control that covers the entire area of your site and covers the entire elevation range of what your site is working through. So don't put all your ground control at just one RL over a map or a mapped area, unless you're working, say, in somewhere like Western Queensland or WA where it's just flat. Then it doesn't really matter. It's just getting the spread out there becomes important. But if you're working in complex terrains and quite steep terrains, you need to have that range of data. The rule of thumb is that ground control points need to be about twice the spacing of what the flight height was taken at. And quite often we would say to people, if you can get people to fly terrain following, that is a far better opportunity and gives you far better consistency in data than just flying a site at one altitude. So the example that's up on the board there is basically come out of a processing report. So we've got ground control point identifications in column A. And then what you see is in here is the ground control point elevation in column D and the elevation of the model at the corresponding same position, okay? The difference between the two is just done by subtraction. And you would look at that, and this is in meters, and you're going, oh yeah, 2.5 centimeters, that's not too bad, because this is a gridded system that we're working with. So you've got a gridded overlay on the model being applied to randomly spaced positions around a site. So these are all good. Then you get down to this one and you go, holy cow, I'm suddenly 70 centimeters out, 69 centimeters out from where I need to be. Why is that the case? You need to go back, and this is one of the checks that you can do. You can go back and investigate that data and see what's actually happened to it. In this case, it just goes back to that image I was showing you before, and it was actually a false error generated by someone putting a ground control point on a block, and the block got flattened, and that was the difference between the ground elevation and the actual ground control position in 3D space. If you read the error on that in root mean square, you're summating all those squared values and averaging them out, you would end up with an error of around about, I think it's 17 centimeters, which is completely inaccurate for what would be expected if you were doing mine-based planning studies. You take that false error out and you're suddenly down to 1.3 centimeters, which is probably pretty good. If you're getting less than 2 centimeters error reported with using a root mean square error, then you can pretty much say that that is a survey grade accurate survey and it's fit for purpose and fit for use. Okay, as I said, look, other factors that affect, and it's not just ground control is one way to test it, but there are other factors that influence that accuracy. Overlap between photographic imagery and your flight path. You need to be in that sort of 70 to 80% percentile overlap range to get things to work. So it's just like the old stereo pair. Got 2 minutes, thank you. Expanding the flight lines will start to cause you error and cause you issues. Think about the use of what you're going to use the survey for. So if you want a survey for geotechnical investigation in an open pit mine, doing a vertically orientated camera is not going to give you what you need. You need to be running camera orientations in oblique patterns and checkerboards to pick up that wall position. So if you're generating point cloud data for ground control management plans, make sure that the orientation is correct. So think beyond what your use is and what other people might want to use this data for. Think about the ground sampling distance. So things like the optics of the camera will influence the quality of the photo that you get. So there's a formula to determine that. You can also just put the information in for the camera that you're using and the flight height you're using, it will give you a GSD. GSDs need to be between 2 and 3 centimetres. So 2 to 3 centimetres on the ground is represented in a pixel in the image to be considered accurate for photogrammetric work. Okay. Utilise reputable providers. Okay. Pay cheap, you'll generally get a cheap result. Okay. Work with someone that's reputable, challenge them on what they're doing. As Mark has said, do reviews, understand the QA/QC processes that they're following. Apply terrain following. Okay, that's another thing. You can fly into a pit, you can get better capture data. Okay, build in redundancy, whatever you're doing. So going with a PPK combined workflow with RTK will give you a better response. If you want to know more, take a photo of that. You can jump online and I'll give you a bunch of information as well. Thank you.
Thank you, James. Thank you, David. Really good presentation. Really appreciate that. Our next presentation now is by James Lally. James is an experienced geologist, having held roles in industry and government with a focus on structural geology, project generation, exploration, and resource modelling. James's talk today is on drilling data quality, more than just samples, and probably fair to say it's one of his hobby horses that we're going to be thinking about today. So we'll just get that presentation up.
Okay, thanks, Mark, and other members of the AG for organising this. Yeah, like I said, this is my little hobby horse I'll be going on about. So let's kick it off. Drilling, quality control, the other stuff. Some of it anyway. Oh, hang on. Do I need to do this? Okay. Okay, so this morning I want to talk about some stuff about drilling QA/QC other than sampling. And this is going to sound pretty basic for this seminar. However, in 30 odd years of dealing with other people's drilling data, this is the sort of stuff that I and my colleagues deal with absolutely constantly. So you're going to hear a lot about QA/QC of samples, and quite rightly so. You need to know how much of something you've got. But the best sampling QA/QC in the world's not going to help you if you don't know where your sample is. And of course, in drilling, that sample location is controlled by two things. Firstly, the drill collar coordinates, and secondly, the path of the drill string as determined by downhole surveys. And both of those, of course, give you 3D coordinates of your sample points. And it's these sort of errors in the collar and the downhole locations, which I'd argue about some of the common reasons for us having to completely exclude drill holes from resource estimates. Because if we don't have confidence in where the samples actually are, we basically can't use them. And these errors are incredibly frustrating because they are so easy to fix at the time that you do the data collection, and so difficult to fix at pretty much any time afterwards, and especially after you've delivered all your data to a third party. Okay, so let's start off with collar locations. So in theory, today, in these days of centimetre accuracy DGPS and sort of metre accuracy GPS, shouldn't really have collar location errors. However, it still happens. And it mostly happens because, again, these really simple basic errors. The first two things, these eastings and northings being transposed and just transcription errors, i.e. just some fat finger typing on the keyboard, is almost always due to the fact that someone's standing out in the field with a GPS, they're reading the numbers down, they're writing their notebook, then they take the notebook and they take it back to their laptop or whatever and put it in the database. Okay, that's what happens straight away. For DGPS locations, it's quite common that they're picked up by a surveyor who's not necessarily with the geologist. The surveyor has to go out in the field after the drill hole's been completed with their DGPS system and pick up the drill hole collar. And at that point, they're normally going to have to tap in a drill hole ID into the next to the location that they've gathered. And that's another point of error, because I've seen databases where someone's clearly just either the survey has basically put in what was written down as a plan hole ID on the little collar tag, or something else has happened, or they've mistyped a number or something, and whatever's happened, so that high accuracy location has now been assigned to the wrong collar in the database. Another one, the wrong or unrecorded projection and datum information for the grid system. Again, you'd like to think that this is becoming less common, but of course, as David just alluded to, of course, when we start talking about swapping over projection datum systems now, this is becoming more important. And obviously, it's got to be consistent in your database as well. Okay, so there's a lot of stuff we get where just somebody says, oh, there's X and Y. So, well, what's the projection of datum? Local or mine grid conversions, well, that's just a whole other nightmarish can of worms that probably deserves an entire talk to itself. So I won't go into it much more about here, but we'll touch on that later. And the other factor is, of course, that there's many jurisdictions now that require complete rehab of a collar position, of collars after they've been drilled. And I've seen some projects where they haven't, especially in remote areas, they haven't been able to get this surveyor out till quite some time afterwards, at which point the actual position of the collar isn't particularly clear anymore. Particularly somebody's had to doze over it and all that sort of stuff. So you actually are losing some accuracy at that point as well. So collar RL errors. Obviously, as David just alluded to, we know that there's different RL accuracy of GPS versus DGPS. So DGPS should be a gold standard for RL accuracy. However, again, we see a lot of projects now, and because of this sort of drone imagery gathering, we actually have very high accuracy DTMs that are now available from either LiDAR or photogrammetry, assuming that they've been done correctly. And these can, of course, be used to correct collar elevation data. Couple of things to note, of course, is that the first thing is that actually check DGPS against the surface to begin with. If you're more than even, say, half a metre out, something's probably wrong. It could actually, of course, be the surface itself that isn't correct, or maybe the drill hole collar's incorrect, okay? However, do be aware of the fact that in some places that your actual drill pad earthworks themselves may have actually changed the RL position of your collar off of the natural terrain surface. So if you've dozed out a pad, obviously you're slightly down. If you'd had to build a platform on the side of a hill, you're slightly up. So you need to take that into account and have it recorded somewhere in the database. Like I said, is the DTM actually more accurate than the DGPS? And you need to assess this as well. So that's part of the QA, QC, probably on both sets of data. RAB and air core holes in particular are usually never picked up with the DGPS. Someone's travelled across the countryside. And what tends to happen then is that all the RLs are assigned some sort of single average, I don't know, what somebody might call sort of a value for the whole program that's meters, or in some cases I've seen tens of meters actually above the natural terrain surface. A lot of these tend to be just left in the database. Now again, there's no need for this. Even in the absence of a LiDAR or a photogrammetry surface, there is still, for most parts of the world, there are contour surfaces available from national topographic surveys that give you the best information. And lastly, don't forget that, again, an example I've seen is that if you have collars drilled from the same pad, they really should have the same RL. So just a little example. Here's a cross-section through some data I received recently. And you can see down here, we've got 3 drill holes that are all intersecting the mineralization, which is this bluish outline here, and roughly within about 10 meters of each other. Don't ask me why they had to drill 3 holes in the same spot. But you can see straight away we've got a problem because we've got this really odd step in the mineralization wireframe. So we investigate further one of these holes. This hole here, for example, we've got an old pit DTM. It's obviously where the hole was drilled from. And you can see that the collar is actually sitting above the DTM. It's also only within about 3 meters of that wall, which is a highly unlikely location for that drill hole to be located and to be able to drill at that depth. So it's clearly got something wrong here. This hole here, again, it's obviously on a pre-mining surface somewhere, so it looks to be okay. Some investigation of the downhole surface of this hole, however, show that every single azimuth from the hole collar is the same, even though the depth's variable. So clearly there was obviously some problem with the azimuth controls, and we'll come back to that, some examples of this again later, that's causing this. And we can see even on that same section, there's another hole that's not affecting this part down here, but that's also elevated above the level of all these other things. Now, obviously, if I keep both of those holes in and keep that wireframe, I'm going to have a very odd-looking shape. It's probably going to mess up some of my volumes in this area, so at least one of these, or maybe 2 of these holes are going to have to go. And the data, this data isn't actually that old. It's probably about 10, 12 years old, but still hasn't been checked properly. And this is done by some of the previous operators of this project. So now it's actually going to be extremely difficult to find out what on earth was going on here. So in terms of the QA, actual quality control of your collar, it's mostly as simple as just looking at the data. So you double check the coordinates as soon as they're available. And not just the coordinates you've written down, by the way, it's the coordinates that you've recorded in the database. Something as simple as just sorting the data by easting the northing will show you very quickly if things have been transposed in some way. And of course, you can have some level of data entry at the database input point, because you can put limits on the easting and northing values that are allowed, which will help a little bit. Obviously, as we discussed, you check RL against a DTM and against adjacent collars. Certainly out in somewhere like West Australia, you expect most of the collars to have roughly the same elevation. So if you find one that's suddenly sitting 10 meters above all the other ones, you're going to be very suspicious. Check that the projection and datum of your collars is consistent with everything else. Obviously, if you change projection systems somewhere along the track, you've got to actually record that in a separate field. Okay, there needs to be a projection datum for every collar location recorded in a separate field. If you are using a local grid, one of these mine grids, it's also important that they are able to be automatically updated when you change the original data. Because if you've captured something in, say, UTM coordinates and there's some sort of grid conversion to it, if you go back during this phase and change everything, you've also got to be able to change your local grid coordinates as well. And again, I've seen lots of examples where one set of coordinates has been adjusted or changed and the other one hasn't, the local grid hasn't. And then last but not least, your other check is like what we just did in that section, which is to check the actual geology for offsets in contacts and mineralization that you don't expect. Okay, next one is downhole survey errors. Now, arguably, I'd say that there's probably more common than the collar errors. And as with modern DGPS things, the modern tools don't necessarily guarantee you error-free data because things happen. Now, clearly, the downhole survey error is going to have a lot more of an impact on deeper holes, because the deeper you go, small adjustments to downhole surveys give you a larger difference in your location. Also, if you're drilling at a low angle to mineralization, So especially in projects where you are limited where you can put drill hole collars and you have to drill down, say maybe, some case 10 degrees, 20 degrees to mineralization, small changes in the attitude of that drill hole are going to have a huge impact on where you place contacts. And the other point there is that, and also where you have very narrow target zones. So obviously this is something that's probably more applicable if you're drilling out narrow vein or even sort of moderately width vein gold deposits than it is to a porphyry copper. However, you still need to be paying attention. So what we tend to see then is we get what was known as dogleg, or an excessive deviation between successive surveys. And that's usually, again, we come back to transcription errors, which is somebody scribbling down the wrong number off the almost legible driller's plod. Okay. And of course, again, this sounds pretty basic to say this, but people using magnetic tools and rocks that have magnetite in them, or pyrrhotite for that matter. Or occasionally what happens, of course, is the driller forgets to drop the tool below the end of the drill rods and just measures it in there anyway. And the final area we see a lot of is using the collar survey as the first downhole survey. Now, generally speaking, this may not be a huge problem. However, there's a lot of instances where we see that it's quite clear that the actual collar orientation is what the planned survey position was. And no one actually checked with the rig. So where you have very large and sudden deviations from the zero depth to the first downhole survey, that's an indication that you probably shouldn't be using that collar survey in your database. It also means that you should always try and attempt to get a first downhole survey as close to surface as you can, so it provides an actual true check on where you start. So here's an example of some data recently of some excessive dogleg deviation, we'll call it. Here's the data of this hole. So you can see we've got a little S-bend. Something's pretty screwy has happened there. This other hole is kind of more subtle curvature, but we can see that these azimuth readings again, the dip's pretty much consistent, but the azimuth readings are suddenly changed by 25 degrees and 50 meters. So again, you'd be querying what on earth went on there. That's not to be confused with the fact, of course, we can have intentional dogleg deviation. And this is an example where somebody used some navvy drilling to keep their drill hole back on course. And these two examples of deviation, we come to, this is an excessive deviation in actual dog's leg, which was caused by a poorly timed jump into the back of a ute a few weeks ago. Now this is an example of the other thing we see, which is basically use of the incorrect instrument. Okay, so here's a bunch of RC holes we've got on a plan view. The red dots are the position of the downhole surveys, and you can see that these red circled holes here have all these huge deviations that start at the collars or 270, and their first downhole surveys around about 290. And it's actually recorded as an Eastman magnetic camera in an area where they have mineralization associated with BIFs. We have some later drill holes that were surveyed with gyros, and we can see that although yes, there's some drift in the holes and deviation in them, it's nowhere near as bad as these things. And realistically, all four of those holes are going to have to be pretty much chucked out. Survey azimuth corrections is the next thing that can be a bit of a confusion, and it's usually because there's some misunderstanding, I'll say, with some people about how to actually apply the correction in the first place. Are you adding or subtracting? What are you doing? Obviously, there needs to be a final azimuth that you're using that is actually the same grid system as you're using to plot the drill holes in. Obviously, everyone's familiar with the fact that you have to have a magnetic deviation correction for declination. Some people aren't quite as aware of the fact that you also need to have a correction to any UTM systems that corrects from true north to grid north, which is called the grid convergence. And the grid convergence, remember, it varies with greater distance from the UTM central meridian and also with higher latitudes. And for historic data, remember as well that in some locations there is a significant deviation, change in declination over time. So here's a quick graphic. Hopefully, I'd like to think that everyone is actually familiar with this, but the key is that when you're correcting things, that there is a sign convention that you start with true north and whatever the grid system you're using, there's positive for clockwise and negative for anti-clockwise. So what you do is you correct mag to true, you add to the declination, and then if you want to get from true to grid, you subtract the convergence. Here's an example of some data from northern Canada showing +3 degrees difference in convergence. So yes, it can be quite significant. And here's some data from, we worked on a project in Cuba recently. You can see even over the last 24 years, there's actually been a 2.5 degree difference in magnetic declination. Other survey errors, again, it's going to sound pretty silly. Depth sign convention, negative down. Don't change everything in the database in case there's a actual underground hole drilled up. And this next one is something that I only actually realized recently, which is a problem with you can get with holes that have only been partially surveyed, i.e. the survey doesn't reach all the way towards the end of the holes. Now, obviously, the impact of this depends a lot on how the holes deviate in the project generally, but there is an issue I'm going to talk about in a second, which is about where we had the last survey, which is a long way from the end of the hole, is actually treated differently depending on what software you're using to plot things up. I'll have a look at that in a second. And lastly, something that I can't cover because I don't know anything about it or enough about it, which is your tool calibration errors. Thank you. Okay, so survey's not reaching end of hole. So here's a cross section through a gold deposit plot up in Serpac. You can see all these drill holes are nicely sort of lifting slightly in dip as they go down. And we can see that there's a pretty well-defined football contact and mineralization that comes up here in a fairly sort of planar fashion. So now pay attention to this drill hole here. So this is the same data plot up in Leapfrog, and this time I've shown where the downhole surveys are taken in dots. And what happens is that Leapfrog takes this last point and it projects a straight line from the last point orientation all the way to the end of the hole. Serpac, on the other hand, obviously takes the last 2 points and continues the curvature. And so what we end up with is the Leapfrog model showing that contact, which now has this weird kink in it, with a difference of about 16 meters between the end of hole position. So be careful. I haven't seen this on what happens on other software packages. I would be quite interested to hear from anyone afterwards as to tell me what other things, how other things treat this. Okay, so the QC quickly. All right, have you picked the right survey instrument? And have you actually done it correctly? So magnetic surveys and magnetic rocks, not a good combination. Have you calibrated the survey instrument? Maybe. Take the first downhole survey closer to the surface as you can. Check and clean up your data after collection. So do this check for the dogleg, what's called dogleg severity, and even just, again, plot things up in a section or a plan. Make sure you record intentional deviation adjustments and check and double check and triple check adjustments that you make from a survey azimuth to a grid azimuth. In conclusion, old man yelling at cloud, probably. However, we do get these impacts on locations of samples and contacts, volumes of domain wireframes, the ability to correlate between holes, and the general sanity of people like me. And like I said earlier, it's so simple, the visual checks at the time of data collection. And last one, Mark, sorry. Remember as well that as we move towards implicit modeling or AI-driven modeling, the estimation or that estimation starts with the assumption that all your data is clean, valid, and in the right place. These grade shell model volumes in particular are affected by sample locations, and you generate these blobs where you don't want them. The modeling systems don't recognize when the data doesn't fit. So coming back to this idea that does it look right? And don't waste those precious drilling dollars by not locating samples correctly. Thank you.
Thank you, James. Thank you very much, James. Our final speaker for this session is Melissa Quigley. Melissa is a spectral geologist with more than 20 years experience in adding value to drill core using hyperspectral mineral characterization techniques to address challenges across the mining value chain. Her presentation is QA/QC of portable IR data for optimal mineral interpretations. Thank you, Melissa.
Good morning, everyone. Can you all hear me okay? Yep. Okay, so I'm going to be talking about QA/QC for portable infrared data for optimal mineral identification. So the quick outline, I'm going to introduce what portable infrared data is and why we need a QA/QC framework for looking at the portable infrared data. I'll go through some quality assurance tips and quality control checks and run through a couple of conclusions. So starting off with what PIR data is. So it's portable infrared radiance data. So it's data essentially collected by handheld infrared spectrometer. It's point measurements, and they're collected from a field of view of approximately 10 by 10 millimeters squared. They're surface measurements, so they only penetrate the top 30 to 100 microns, and they're typically collected with the spectrometer in contact with the sample, be it core, chips, or powders. So the infrared spectrometer measures reflected light across the 350 to 2500 nanometer wavelength range of the electromagnetic spectrum. That covers the visible, near, and shortwave infrared regions, and it does so in thousands of very narrow contiguous wavelength channels. And if we're to plot up the reflectance for each of the wavelength channels, we're able to create a line graph or a spectrum, and that spectrum contains absorption features, troughs, that occur at specific wavelengths, and we're able to identify what the mineralogy of the sample is based on recognition of where the absorption features are occurring. So there's different processes that take place for these features to be generated. In the visible near infrared, it's typically electronic transitions, changes in energy states. And in the shortwave infrared, it's molecular vibrations that bring about these absorption of energy. So the example on the screen is the muscovite and chloride, with the arrows identifying for the 2200 feature is the typical feature that we refer to identify any of the aluminium hydroxide bearing minerals. And the two other arrows here around 2340 and 2250 are identifying chloride. So some of the benefits of using portable infrared data is that it's fast. You can collect measurements in 30 seconds. It's non-destructive, so you retain the integrity of the sample. There's no sample prep, or it's minimal sample prep. You want to make sure that the sample's clean and dry. You know, I'm going to mention that several times because it's really important. You want dry sample to maximize the reflectance. If it's damp or wet, it subdues the overall reflectance, and that just hinders your ability to interpret the mineralogy. It's a non-hazardous technique. There's no safety certification required to use portable infrared data, spectrometers, and they're cheap. And I know that's a relative term. So we're looking at, depending on the type of spectrometer that you're going to use, 25 to 100K for each unit. They're small, so they're easy to deploy to site or in between projects, or even to take out into the field. And they're readily available to purchase from a range of different manufacturers listed on the screen. So PIMA is listed there. It's not the manufacturer, but it's just, there's a range of different spectrometers available, and PIMA, that was created 20 plus years ago, is still out there. They're not making them anymore, but it's such a robust little system that they're still good to collect data. So when we collect these hyperspectral point measurements, the goal is to be able to generate good quality mineral results in a database-ready format. And to do that, you need to have good quality data to start with. So we need to have these QA/QC strategies in place to collect and check the data and to help us achieve that goal of generating the high quality mineral results. And this is regardless of whether you're doing a very basic approach of manually interpreting a spectrum at a time, or if you're using more advanced techniques like machine learning approaches that are processing thousands of spectra. And just my definition of good quality data, it is data that has a strong signal, no artifacts such as plastics or driller's grease that can compromise the spectral integrity of the data. You want minimal noise and clearly resolved mineral features in the spectrum. So the quality management system that's comprised of quality assurance and quality control steps will be defined by different people in various ways today. I like to keep it very simple and explain it in a way that talking to someone at the pub is able to understand it. So quality assurance is defining a set of procedures to accomplish a task. It's what you need to do to collect good quality spectra. These steps for collecting the good quality spectra should be documented in a protocol that stipulates what needs to be done, and how it is to be done should be spelled out in very clear, simple terms in the standard operating procedure. And they are instructions for performing repeatable routine tasks. They should be discussed amongst the team. They should be easy to understand. And you should be open to updating them as new information or new ideas come into play. The aim of the QA program is to prevent problems. This is different from the QC part of the program, which is to identify the problems. So you're looking to check that the spectra are of good quality and identifying any problems or compromised spectra. So I'm going to run through a sort of a setup program for planning your QA strategy. So you need to have the workflow in mind, what steps are going to be followed to plan it accordingly. And you need a purposeful space to do this in so that you can make sure that you can work efficiently, reduce any potential errors that are typically human errors at this stage, and increase the productivity. So safety is going to come first. Clear the space for loading and unloading of core trays. It sounds very simple, but it needs to be stated. Make sure there are no trip hazards in place. Ensure the samples are clean and dry and in order. So whether it's core tray orders or sample ID orders. And you want to make sure that the spectralon, which is the white reference panel that we use to do baseline corrections of the data, is clean. It's got to be very clean to do a good calibration against it. Hard to maintain when you're in an active exploration camp or mine site. If you need to clean it, you can use very fine-grained sandpaper under running water and let it air dry. If you've got fluorescent lights overhead, best to turn those off because they actually impact on the spectral reflectance if you're not using a contact probe. If you're using mains power, that's great. If you're using the battery-charged spectrometers, make sure the battery is fully charged before you start and have the spare one ready to go. And at the end of the day, make sure you've got it on to recharge for the next day. I'm going to run through some of the quality control, quality assurance tips for collecting the data. So I'll break it down to equipment and the data acquisition software. So for the equipment, you want to make sure that all the cables are correctly attached, and this is instrument dependent. So things like the halos don't have the cables, TerraSpec 4s do have the cables, and there's a connection at the back of the TerraSpec that sometimes isn't connected properly that can create electronic noise being displayed in the spectra. So it's those sort of connections that you want to be sure that have been tightened but not over tightened. You want to allow a warm-up time of about 20 minutes for the instrument, and this is for the internal detectors to stabilize. They're thermoelectrically cooled detectors. Some people say 20 minutes, some say 30 minutes. Play it safe, minimum of 20. The data acquisition software will perform the white reference calibration using the spectralon that you've measured. This should be done at the start of the day and at regular intervals throughout the day, probably around every 20 minutes. You should set the sample count to 100, and this will create a 10-second integration time. The 100 sample count is the internal averages. So the more internal averages that you do, reduces the noise in the spectra. You can set up the file name to make it simple to record details about the spectra. So I like to include the drill hole ID and the depth that the measurement was collected at for drill core and chips. And you might have, depending on what software and what instrument you're using, you can have it set up to automatically increment. So if you're collecting regularly spaced measurements, 1 meter spacing down hole, it makes a very efficient workflow. The main point here is to be very methodical, very systematic in how you are collecting the data and how you are naming the data. And you want to be able to collect a spectrum of a mylar sheet, which is a plastic sheet with very sharp multiple features at known wavelengths. And you can store this either with the data set you're collecting that day or in a separate folder, so that every day you're collecting a mylar. This is your standard that you're able to track for any shifts, drifts in the wavelengths of these key absorption features. If you store it with the year, the month, and the day, then you can sort the files in an orderly way as well. And measuring the mylar is one of the ways that you can be confident in the data that you're collecting. You want it to be data that has a very good wavelength calibration. The mylar sheet has 9 channels that are checked. You measure the mylar placed over the white spectralon panel, which is the circular panel on the screen there. The wavelengths that you're going to check for are included on the mylar sheet down the bottom there. On the right-hand side is a combined rare earth element and mylar spectrum that we use for checking 28 absorption features for drift over the 350 to 2500 nanometer range for instruments that are hired out from IMDEX, and this from a colleague in the US. So quality assurance, I'm going to run through some tips for collecting high quality spectra from soils, field samples, drill core, chips and powders. You're going to hear this multiple times. The sample must be dry. To collect good soil samples, you want to collect it from the B horizon to avoid organics, and you want to sieve the sample to remove any debris. You can put the sample either in chip trays or in a Petri dish or measure it directly in the field. Just be mindful of cross-contamination. You either have to clean the contact probe between measurements or the Petri dish. For collecting field samples, again, sample's going to be dry. So be mindful of the weather conditions when you're going out into the field. You may choose to collect a measurement from a fresh and a weathered surface. Either way, make sure that there's no algae or any organic material on the surface of the rock sample. If you're collecting grab samples, it's a good idea to collect multiple measurements of the one sample, and this is to ensure that you're achieving good representation of the mineralogy in the sample. If you've got samples that have coatings over it, such as resin, or lacquer. Sometimes you see core blocks at a mine site that have been mounted up to give an example of what the different lithologies are that you're encountering. If they've been coated with something, you can't collect a measurement over that coating because it's got its own spectral signature and it'll compromise the accuracy of any of the mineral interpretation. From drill core, you want to make sure, again, that the surface is dry and clean. Sometimes you can get different minerals precipitate on the surface of drill core, such as gypsum. Is that 5 minutes to go? Oh my God, okay. And you want to make sure that you've got good contact between the contact probe and the surface of the core. So whether that's full core or split core. Avoid any of the markings, ORI lines, text. They've got their own spectral signature. Record the depth ideally in the file name. And you can mark the core where it's collected, either a tick on the side or a circle around where you collected the measurement. The sample spacing can be governed by what the objective of the study is. If you're doing a vein study, it'll be irregular spacing. If you're going to map deposit scale alteration, you can do 1 meter increments. For drill chips, you can measure the chips in the actual chip tray. Just make sure that the spectrometer is in touch with the sample. You can spoon it out into a Petri dish and use a mud light to measure the sample from beneath. Don't measure in plastic bags, and cross-check the file names with the depths on the lids. For powders, it's actually the least preferred sampling medium. It has very fine grains that scatter the light between the particles, and there's the potential for loss of mineral information in a homogenized sample. You can empty the packets into Petri dishes or chip trays to measure them. Again, be mindful of cross-contamination. Ensure you've got adequate coverage so that you're not getting any of the reflectance of the plastic tray underneath. Whichever sampling media you're going to use, stick to it. If you're going to just be collecting spectra from powders, stick to powders, because the depth of the feature changes according to the grain size as well. So this example shows a comparison of the same rock as core, then a crushed version and a powdered version. And you can see the top measurement from a powdered sample, the overall reflectance is higher, but the depth of the features is shallower. So it's a good idea to stick to the same sampling medium. For quality control, you want to have a system that's going to check parameters such as noise, low reflectance, wetness, or spectrometer errors. This is an example of AICIRIS Desktop, which is a product that Index puts out. AICIRIS is a service for the automatic processing of and mineral interpretation of portable infrared data. It's a cloud-based service. Customers have free access to the desktop to check the quality of the spectra. And it provides a way of auditing the data, bringing in the metadata, and retains that traceability of the information collected with the data. We have a color-coded traffic light system shown in the bottom left, where green is good. We have a QA/QC status window down here. With all the boxes are green, everything's good. If it's yellow, it's borderline. If it's red, it's a major problem, and we flag that for you to have a look at. I've got a bunch of different problematic spectra to show you. Essentially, the top spectrum is an example of what a good spectrum looks like. The middle one is okay. It's got a little bit of noise at the end. This is the jaggedy lines. And the bottom one is like a catastrophic fail. It's an instrument malfunction, so you've got a lot of red boxes there. If you've got a dirty spectral on, you'll get inverted peaks. That will prevent you from identifying the mineralogy correctly. If you've not calibrated your instrument correctly, you will get these straight stretches of lines, or you may get a saturation where the spectrum is going, the reflectance values are going over 1. If your connection with the cable on the back of a spectrometer is not secured, you can get these wavy lines in the spectrum, which is electronic noise oscillations, and just flags for you that you need to adjust the cable. What to do if you've got problematic spectra? Basically, you just have to delete it and remeasure the sample to acquire good quality data. So in today's presentation, I've introduced you to portable infrared data. I've explained how we interpret a range of minerals from the reflectance features in the infrared data and the types of minerals that we can identify. I've gone through and reviewed some of the quality assurance steps to acquire good quality portable infrared data from a range of sampling medias, from powders, chips, drill core, grab samples, and soils. I've gone over some of the quality control measures that we look at to make sure that we're collecting good quality data. Things like making sure you've got a minimum reflectance, minimal noise in the VNIR and the SWIR, that the sample is not wet, that you don't have any calibration issues or spectrometer malfunctions. And a message that I really want to stress is about the importance of being systematic and methodical in everything that you're doing in this hyperspectral point measurement program for core logging or chip logging. You need to have a correct setup. You need to be consistent with your file naming system, the nomenclature, and calibration. Keep on top of the calibration so that you get good quality data. All these steps should be documented in protocols and SOPs and should be freely discussed with the team. Always seek feedback and revise periodically as new information or new ideas come to light. Use a system for data auditing and storing metadata and traceability of that information. AI Cyrus is the information that I've provided today. It's a great framework to achieve that. Plus, it's a system that delivers the mineral identification results and associated parameters like compositional substitution, crystallinity, variations, and abundance variations. But that's another talk. So the main message is collect good quality data at the start to generate reliable mineral results. And this is to lead you to making informed and confident decisions and developing new ore body or rock knowledge. Data, information, knowledge. Bang.
Thank you, Melissa. David, and do you want to come up? So thank you very much, Melissa. Just stay there. We're going to move into some questions and answers. We will share the microphone. Peter, have you got any questions coming through? But we might switch this on. Okay, so 3 excellent presentations. I'm going to be the wandering person with this microphone. Peter is going to pop up with any questions that come on from online, but if you have any questions online, please send them through the Q&A. We have a question from Rob.
Hi, my question is for Melissa. That was a fantastic presentation. My team are we do ASD on all of our samples, and my team is convincing me to build an air-conditioned room to do the ASD samples. Is that required, or does it get hot and start deviating, or are they just tricking me?
Who do you work for?
I work for Merdeka Copper and Gold. So it is a tropical environment in Eastern Java.
Right. Okay. It does help if you can maintain a consistent environment that you're collecting the measurements in. And, you know, I come from CSIRO, working there for 15 years, where everything was done properly. And one of those things was having a controlled environment to collect the data. That being said, you can collect the data out in the field, in the tropics, in the, you know, colder parts of the world as well. But ideally, if you've got this consistent temperature, humidity environment to collect the measurements in, the more stable the instruments are going to stay and the better quality data. So go for it. Yeah, they're not whinging. They're quite correct.
Thanks, guys, for a great presentation. It's Renee speaking here. James, I'm looking at you for a question. Great presentation, love it. Everything is in there. I got one question and one comment. The comment is on the way Leapfrog shows the curves, because there's 3 settings. I'm sure you're familiar with them, but different softwares indeed do different things. You got the balanced tangent, the raw tangent, and the spherical arc, and it's probably the default that shows that. The question is, and I think it's going to come up often today, regardless of all the quality, when is it good enough and for what? And I can explain what I mean, but I'm sure you know what I mean.
Yeah, no, that's
Because we're running resource
no,
estimates.
that is a good point, Renee, and it does come down to this thing about, you're right, is that data fit for purpose? And in that particular example, for instance, you know, we can see that we were generating this rather dubious looking shape in the interpretation. And yeah, look, to be honest, I mean, on the global scale of the resource estimate for that deposit, probably is not a material impact, no. But I think it's more the fact that you need to be aware of these things to understand that, like I said, it would impact, however, I think probably more so if you start using implicit modeling, and we see a lot of people using grade shell models as proxy for domains. And when you start applying that sort of thing, those errors in grade shell models, I think they will tend to blow them out even more. So I think, the question of how, I guess what you're saying is how sort of relevant it is I would say it depends. So yeah. Yeah. And just coming back on the thing about what you said about the like the different settings in Leapfrog. I mean, surely there's the different settings you use for drill holes versus trenches, sure. I didn't see that I actually haven't seen the other setting you can change to. Yeah, they probably are. I've only managed to test that. I tested it with Geoscience Analyst, which I know is a free viewer, and that does the same thing as it's a Leapfrog, sorry. So clearly different software does different things.
A question. I notice there's a lot of database geologists in the room. I'm curious about this from Mark's perspective. The one that you had the front there, we had the little steps, and you had the blue circles for the different data types, and on the top you had professional opinion, I suppose, in trying to apply these QA/QC principles to the data itself. What's your view in terms of trying to entrain those QA/QC processes into the database, so away to some degree from the individual speculation that can come through in the process?
Thank you, Jared. I think that there's ways to embed confidence into your database. And, you can see that in both survey data, assay data, logging data, where you can actually add confidence fields to say, I am very confident about this data point, whatever it might be. I am sort of happy with it, and this is bad data and should not be used. So there's a pretty simple way to do it in the database, whichever database you choose to use. So that helps with that. Your sort of comment also was QA/QC up in the analysis stage. And that's really important to be able to then say, well, what techniques are we using to analyze the data to make sure that we are comfortable with it? And that often gets skipped. So I totally agree with that. Peter, do we have any online questions yet? Come on, everybody online. I'm sure you have some questions. We have a question over here, so we'll move over to Nick.
Thanks everyone for all of the presentations were great, and all of those aspects in some of the work that I do, obviously it really rings true. And I suppose an underlying comment that perhaps all of you have slightly made, and one that is going to become much more important, and I want to get your thoughts on it, is with the use of AI, and as we move forward with the use of analyzing and machine learning big data, it has become so much more important to make sure that the QA/QC process is so important, because especially at this stage, it's so reliant on the data that it sees coming in. So making sure that those QA/QC steps come in, like you made a point of the GCP points, and making sure that when you talk about colors and the colors that you may be using for those, that consistency also has to be measured, not just even the position of the GCP point. So I just thought that, how do you all see this sort of new technological change come in regarding, the importance of it's a reasonably big question, but.
As an old hand of the game, I don't think AI is going to replace us.
Yeah.
I think people that, and I suppose I've seen it, I've worked in computers for over 35 years in computing geology. You can automate everything if you want to, but at the end of the day, a lot of it comes down to common sense. And I'm not sure, and I'd hope to be proven wrong, but I don't believe AI is going to be the savior that everyone thinks it might be.
Yeah, I'll agree. And I think it comes back to this idea that Mark touched on as well earlier, which was the idea of the sniff test, about, as an experienced practitioner, when there's something not right. And some of that stuff I think is quite difficult to program or even a machine learning system to necessarily pick up on, probably because of there's a lot of nuance involved, obviously. And even like things I showed about the downhole surveys, for example, clearly there's instances where something's intentional, that would be necessarily flagged as being wrong, and other instances where something is clearly wrong but wouldn't necessarily be flagged as such. So you've got this. This is possibly, I think, a bit too subtle, the systems available at the moment.
I'm going to buck the trend a bit here and say it's here and it's about how you use it. And it depends on using the right tool for the task. So no, we're not going to be replaced, but the use of AI or machine learning techniques is meant for my purposes to automate a lot of the steps that are repetitive in nature. So you still need a geologist to understand the mineral results at the end of the day. What we're doing is automating the process from once the data is collected to generating the mineral result. And then it's up to geos to put it in context, whether it's for an exploration or, you know, mapping out the alteration across a deposit. Mapping out your lateral and vertical distribution of certain alteration minerals that are going to allow you to determine proximal and distal mineralogical relationships with the ore zone, or geotechnical purposes, identifying swelling clays, geomet purposes, providing sufficient representation downhole. One of the known sort of problems with geomet studies is insufficient representation of the data, and then you get the surprises at the mill. So collecting a lot of data, processing it in a very consistent, methodical way. We really benefit from using AI for doing that at Index using AI Cyrus. Yep.
So just to follow up on that, Melissa, is it fair to say that you're currently using those techniques in the QA/QC of the infrared data?
We use the QA/QC checkboxes in AI Cyrus Desktop, the free app, to check the quality of the data. So it's still a manual process where the operator or the customer who's uploaded the data needs to check those boxes. So we automatically flag things that can be detected in the spectra, a certain number of things. There are still some extra things that we would like to add to improve that QA/QC checkbox. But the processing of the data is what is largely automated now.
Okay, excellent. Thank you. And another question.
Thank you, folks. My name is Abdul, and I work at the MEC. My first question goes to you, Melissa. With the data that is collected here, how successful is it in terms of bulk minerals as against precious minerals?
Bulk minerals versus precious minerals. Okay, so we don't identify the sulfides. Very good point, because I realized I skipped that on one of the slides. I mentioned a range of different minerals that we can identify, and I had a comment at the end saying not the sulfides. So sulfides typically are aspectral in the VNIR spur regions. They don't reflect well. They absorb a lot of the energy, and you can pick up various things like if it's oxidized bornite, you could pick up a purple peak, pinky, bluey, purpley peak in the vis, but we're not identifying it because it's not unique. So we've got to take into consideration the non-uniqueness of the spectra. So sulfides are not something that I would advocate, or magnetite.
Right. I guess it's effectively answers my follow-up. I was going to ask if you're looking for fine grain gold as against the coarse grain, how is that going to play up with the infrared?
Okay, so not picking up the gold, but picking up the alteration minerals associated with it. So if you've got fine grain white mica, sericite associated with it, or if you've got quartz carbonate veins, we'd pick up the carbonate. So it's really the minerals that make up the bulk of the deposit that we're able to identify. So the gangue versus the ore minerals.
Thank you.
You're welcome.
James, I'd like to pick your brain on this. I had a huge data set that came from a super mineralization. We're talking about up to 70 meters or 80 meters. The issue was the color location, the color of the individual drill holes. Because over the years, the data had gone through various transformations from mine grade to, to the UTM, and then you know exactly what I'm driving at. Now, it became very difficult to actually ground truth the individual drill holes. Now, you will pick a drill hole in the database, walk to the field, and then you are literally 20, 30 meters away from there. What I did was that I had to do what I call proofing the drill holes, try to plant drill holes to sort of mimic the mineralization. That's what I did. But I would like to pick your brain on what you would have done different.
I mean, well, it's always the tricky one without having seen the data, but I mean, there's a point at which you can only go so far. And like you point out with old data, anything, you know, if it was pre-DGPS, you may be able to track down some of the very, I would try and track down the very earliest reports, and if there's some sort of map that shows the collar positions relative to some other features or something like that, then fine. At the end of the day, though, there's a point at which you're going to have to say, oh, look, I'm going to have to say that there's a level of uncertainty on the collar locations, on the location of the samples. And if that's the case, that's actually something you can then use. That uncertainty would flow through into your resource classification. Because one of the points of saying, if you've got measured or indicated resources, one of the points of certainty is about you know, being able to correlate with drill holes and their position. So once you start downgrading positional accuracy, realistically, the best you can probably do is say, well, it's going to be inferred for a start. Now, it almost doesn't matter how close together things necessarily are. If you're not certain of their locations, you're going to have to downgrade the resource. So yeah, in that respect, yeah, I mean, you just can't, you would just have to kind of do the best you can. But there is a point, of course, at which you have to say to a client who's got all this old data, you're going to have to go out and re-drill at least, or not re-drill, or sort of twin some of these holes to actually confirm positions and do this stuff. So that's what I'm saying, is that without, there are instances where either positional accuracy from the collar location or the downhole survey means you've got to say to that, say, I don't know where this hole is, and I'm going to just not use it anymore. And that's what we've commonly done in areas where we've got lots of historic drilling. Yeah.
And I think that will generate a discussion that could last the whole rest of the day, just in itself, which
Right.
we don't have time for. Fantastic session. We will be back here at 11:10, and we will be starting the first presentation at 11:10, whether you're in here or not. I'd like to thank all of our speakers today in this first session, which is really important because these are all the sort of data inputs that will feed into the conversations that we have in the second session. But these are really, really important issues. And I'd like to thank all the speakers today. Thank you.